Welcome to Introduction to Ecology, Lesson 7. As in last class, the focus of today's class will be population dynamics, trying to understand how populations of organisms change through time. So just a bit of review. In last class, we talked about life tables, and these were tables summarizing survival rate, survivorship, and fecundity as a function of age or stage. And what these life tables allowed us to do was take the number of individuals in a population in each of the different age classes and use that to predict what will happen to the population 1 year from now, 2 years from now, 3 years from now, and so on. So again, a little review. If we want to know the number of age 1 individuals next year, we are going to look at the number of age 0 individuals this year and multiply that by the probability that those individuals survive until next year. And so in this particular example, I have 10 year 0 individuals. They have a 10% chance of survival. And so I get one individual of age 1 the next year. If I want to know the number of age 2 individuals next year, I'm going to take the number of age 1 individuals this year, multiply it by the probability that they survive, in this case 90%, and so that's going to give me 18 age 2 individuals next year. Same thing for age 3. If I want to know the number of age 3 individuals next year, well, those individuals are age 2 this year, so I have to take the number that are age 2 this year, multiply it by the probability that they survive, and that gives me 12. So I should have 12 age 3 individuals next year. Finally, with age 4 individuals, there's no probability of an age 3 individual surviving, so I have no age 4 individuals. And so we were able to fill out that life table, predict the number of each different age next year, except for our newborns. And remember, to predict the number of newborns, we needed to look at births, and we needed to look at the number of babies each individual in each age class had. So I have to take my fecundity for my age 0 individuals and multiply that by my number of age 0 individuals, my fecundity for age 1 individuals, multiply that by my number of age 1 individuals, fecundity for my age 2 individuals, multiply that by my number of age 2 individuals, my fecundity for my age 3 individuals, and multiply that by my number of age 3 individuals. And so if I do that, in this particular example, I get 900 newborn babies next year. And so that gives me the number of different individuals in each age class 1 year later. Of course, I can then take that, slide it over, and predict the number that's going to happen 2 years later in the same way. So again, I predict my number of age 1 based on my number of age 0. I predict my number of age 2 based on my current number of age 1, and so on and so on. And then, of course, I predict my number of newborns based on fecundities. And that gives me the number of different organisms in each age class in year 2. Again, I can move that over. I can go on and on and on, predicting year 3, year 4, year 5, year 6, year 7, year 8. And you should be able to do that. All right. So that is basically how I predict the number of individuals of any age from 1 year to the next. But then in the last class, we talked about age ratios and stable age distributions. So now we're going to look at that in a little bit more detail. When I talk about the ratio of two different ages, say age 1 to age 0 individuals, I'm going to look at my age 0 individuals, I'm going to look at my age 1 individuals, and I'm just basically going to calculate a ratio. I'm going to divide one by the other. So if I want the ratio of age 1 to age 0 individuals, in year 0, I have 20 age 1 individuals, I have 10 age 0 individuals, and so my ratio is about 2 to 1 or 2. 1 year later, though, it's a little bit different. I only have 1 age 1 individual, and I have 900 age 0 individuals, so I get a much smaller number, 0.001. Year 2, things have sort of stabilized a bit better. I have 90 age 1 individuals, 260 age 0 individuals, and so my ratio is about 0.35. And again, I can go on and on and on doing this ratio, calculating the ratio of age 1 to age 0 individuals over a pile of different years. Now, the interesting thing with these life tables is that if you do this over and over and over, one year after the other, and you plot it, what you'll notice is that eventually that ratio will become constant. So, after about 10 years here, you see that line, that ratio of age 1 to age 0 individuals is basically a flat line. It's the same from one year to the next. And so basically that ratio becomes fixed at 0.062. And after sort of a long time, in the long time limit, I have about 0.062 age 1 individuals for every age 0 individual. I can do the same kind of thing with different age classes. I could look at the age 3 to age 0 individuals, the age 2 to age 1 individuals. Here I'm just going to show you with age 3 to age 2 individuals. It's just a different ratio for two different age groups. So here's my age 2 individuals, here's my age 3 individuals, and again, to calculate that ratio, I'm just going to divide the number in one age class by the number in the other. So I have 40 age 3 individuals, 30 age 2 individuals, my ratio is 1.33. 1 year later, it's different. I have 12 age 3 individuals, 18 age 2 individuals, and so my ratio is 0.67. 1 year after that, I've got 7.2 age 3 individuals and 0.9 age 2 individuals. My ratio is 8. And again, I go on and on and on. But once again, if you take a look, if we plot the ratio of age 3 to age 2 individuals over a pile of years, what you'll notice is that just like the other ratio where we were looking at age 1 to age 0, this ratio stabilizes. It becomes a constant value, a flat line, after again about 10 years. And so in this case, we find that we flatline at about 0.25. So we have about 0.25 age 3 individuals for every age 2 individual. All right. And so again, typical of these life tables, this will always happen with these life tables. If you calculate enough years out, if you calculate, sometimes it's 10 years, sometimes it takes 20 or 30 or 100 years, but if you calculate the sort of age distributions for enough years, you'll eventually find that these ratios stabilize. And we see that in the first figure we get a flat line after about 10 years, in the second figure we get a flat line after about 10 years. So when those ratios stabilize, when they become the same value 1 year after the other, we say that the population has reached a stable age distribution. So that's the age structure of a population whose age distribution does not change from 1 year to the next. In other words, those ratios of age 1 to age 0, or age 2 to age 0, or age 1 to age 2, or age 3 to age 2, all of those ratios, no matter what ratio you pick, it's the same from 1 year to the next. And that's when the population has reached a stable age distribution. If even one of those ratios changes, the population is not at a stable age distribution. All right, so again here, we've reached that stable age distribution in around 10 years, slightly later than 10 years. All right, just because the population has reached a stable age distribution does not mean that the population isn't changing. So we can still have what's known as population growth. So here, if you take a look at the number of age 0 individuals through time, you'll notice that it's changing quite rapidly. We go from 10 individuals to 900 individuals to 260 and on and on and on, and then it starts to get really, really big. We're getting into the thousands and the tens of thousands, and if you sort of plot that out for 25 years, you're getting up to 10 to the 7 individuals in the age 0 class. And so again, the number of age 0 individuals starts to grow very, very rapidly. Same exact thing if we look at age 1 individuals. We start with 20, it bounces around for a bit, we get down to 1, and then there's 90, and then 26, but then eventually it starts to sort of take off, and we get 408, 970, and again, if we plot that, within 25 years, we're growing rapidly up to 10 to the 6 age 1 individuals. So again, after a little bit of bouncing around, the number of age 1 individuals starts to grow really, really rapidly. So that's looking at individual age classes and how they're growing really rapidly. If we take a look at the total population, we can do that pretty easily by summing up all of the age classes. So if I sum up my 0 to age 3 in this particular population, that's all I have. I do that for all of my years, and I plot that total against time. Again, you see that exact same trend. You see maybe a little bit of bouncing around at first, but after a few years, the population starts to take off, and it really starts to grow very, very quickly. All right. So the reason these populations are growing really quickly is because we have what's known as geometric growth. And to understand geometric growth, the first thing we need to do is calculate population growth rate. So the year-to-year population growth rate is the ratio of the number of individuals in year t plus 1 to the number of individuals in year t. And so here, for example, if I look at the number of individuals in year t plus 1, which is year 1, and I look at the number of individuals in year t, which is t equals 0, then that ratio is 9.31. I can do the same thing for 1 year later. I can look at the number of individuals in year 2, divide that by the number of individuals in year 1, and that will get my year-to-year growth rate for years 1 to 2 as 0.38. Do the same thing for year 3. I take my number of individuals in year 3, divide it by my number of individuals in year 2. That gives me my population growth rate going from year 2 to year 3. Again, one more time, I could take my number of individuals in year 4, divided by my number of individuals in year 3, and that gives me my population growth rate going from year 3 to year 4. So I keep doing that on and on and on, over and over and over, and it's probably not going to come as a big surprise to you, but if I look at those population growth rates through time and I make a graph, just like my age ratios, I see that the population growth rate bounces around at first, but eventually it stabilizes. It comes to a constant value, so it's the same 1 year after the next. The population size is not the same. The population is growing, but the rate at which it's growing, the sort of size 1 year divided by the size the year before, starts to become a constant. And so in this particular case, it becomes 1.62. That population growth rate, that year-to-year population growth rate, plateaus or flatlines at 1.62. All right. Now, that was looking at the population as a whole, looking at the growth rate of all the age classes summed together from 1 year to the next. We can also look at the year-to-year population growth rate of a particular age class. So let's take a look at the age 2 group. So again, I can calculate the age 2 growth rate by taking that final line should say age 2 growth, not age 3 growth. I can do the same exact thing. I take the number 1 year later, so in year 1, I divide it by the number now, so in year 0, and I get a ratio of 0.6, so that's my population growth rate for my age 2 individuals. Same kind of thing for the next year, going from year 1 to year 2. I take my number of age 2 individuals in year 2, divide it by my number of age 2 individuals in year 1, and that gives me my population growth rate for my age 2 individuals going from year 1 to year 2. Another year, I take my number of age 2 individuals in year 3, divide it by the number I had in year 2, and that gives me my population growth rate for age 2 individuals going from year 2 to year 3. Again, I just keep doing that, and again, if I plot those population growth rates for the age 2 class against time, it also stabilizes. It bounces around a lot at the beginning, but it stabilizes. And the really interesting thing here is that that age 3 growth rate stabilizes at 1.62, which is the exact same growth rate as the population as a whole. And that's not actually a coincidence. You have the same long-term growth rate whether you look at an individual age class or a total population. And that's always, always, always going to be true once you reach a stable age distribution. The population as a whole and each individual age class grow at the same rate. So with these life tables, that will always be true. As soon as you reach a stable age distribution, your population will grow at a particular rate, and each age class in that population will grow at the same rate. That's the only way that you can keep those age ratios constant from 1 year to the next. If they all grow at the same rate, they're all kind of growing in step together in the same way. All right, so that's population growth. But we all know, unfortunately, that not all populations grow. Some populations, in fact, decline. And so we're going to look at the exact same example we started the class out with. But the only difference is, in this case, I've changed my fecundities in my different age classes. These fecundities are actually a lot lower than the example we started with at the beginning of the class. Everything else is identical. So we're going to do everything exactly the same as we did before. We're going to predict the number 1 year later based on the number in the current year. So the number in the current year is that nx in the first column, or the second column actually. And then we're going to predict the number 1 year later. And so same kind of deal. We're going to say, well, the number of age 1 individuals is equal to the number of age 0 individuals now times the probability they survive. The number of age 2 individuals next year is equal to the number of age 1 individuals this year times the probability they make it through the year. The number of age 3 individuals next year will be equal to the number of age 2 individuals this year times the probability they make it. And then, of course, there's no age 4 individuals because there's no probability of surviving from age 3 to age 4. So that's all identical to the example we did at the beginning of class. But now let's take a look at that fecundity, and those fecundity values are different. So if I take the number of babies that the age 0 class has times the number of age 0 individuals, the number of babies that the age 1 class has times the number of age 1 individuals, the number of babies that the age 2 class has times the number of age 2 individuals, and so on. I add those all together, and what you'll find is that I get 90 newborns. That's a lot smaller than I had before. All right, doesn't look bad. 90 is a lot. We'll just put that in year 1. We'll slide them over. We'll rinse and repeat, do the same exact thing. But what you'll notice is if I do exactly the same thing as I've always done with these life tables, I predict the number in year 2, and then I use that to predict the number in year 3, and I use that to predict the number in year 4, on and on and on and on. What you'll notice is those populations aren't blowing up. The numbers in my age classes, in my age 0 classes, not suddenly getting really, really big as I sort of move out towards year 8, 9, 10. In fact, it's getting smaller and smaller and smaller. And that's happening in all of my age classes. And so if I take a look at my total population, I sum up the age classes in each year, what I find is that the total population is also getting smaller and smaller and smaller. Instead of like the previous example where it's getting bigger and bigger and bigger until it was like 10 to the 7th individuals, in this case I started with 100, and by the time I reach year 8, I'm down to about 3. And so again, I can plot that, and you'll see exactly what I said. There's some bouncing around at the beginning, but by and large, as we move through time, that population crashes. And so this particular example, like I say, was identical to the example we started the class with. The only difference was we had lower fecundity. And because of those lower birth rates, instead of having a rapidly growing population, we actually end up with a rapidly declining population. All right, so let's do the same thing we did before. Let's calculate population growth rate. Exactly the same. To know the year-to-year population growth rate, we're going to take the number 1 year later and divide it by the number in the current year. All right, so that gives 1.21 for the year 0 to year 1 population growth rate. If I take a look at the population growth rate going from year 1 to year 2, I take 43 and divide it by 121, and I can go on and on and on. Again, if I plot the population growth rate over time, we see the exact same trend. We get some bouncing around at the beginning where we aren't at what we term equilibrium, right? Crazy stuff happens. But then eventually we settle down and that population growth rate becomes constant from 1 year to the next. But here's the kicker. Look at the value that we've sort of settled in on after about 10 years. In the example we started the class out with, the population growth rate settled in at about 1.62. But in this example, the population growth rate is actually constant at 0.62. And that's an important distinction. When the population was growing, the population growth rate was 1.62. Now that the population is declining, the population growth rate is much smaller, it's 0.62. And so you might wonder, well, where's that threshold between growing and declining? And it just so happens that that threshold is 1. So when the population growth rate is above 1, the population grows exponentially. So 1.62 is well above 1, and so we have that rapid rise in population through time. When the population growth rate is less than 1, the population declines exponentially. And so you have this massive rapid crash. And again, 0.62 is much less than 1, so in that scenario we saw the population declining. So basically, whether you have a growing or a rapidly declining population depends entirely on that population growth rate. And the population growth rate depends on fecundity, like we saw in this example. All I changed in the two different scenarios was the number of babies that the individuals were having. So population growth rate depends on fecundity. It also depends on survivorship. The better the organism survives, the more likely you are to have a high growth rate. All right, and again, if you had your population growth rate exactly at zero, or exactly at 1, I'm sorry, then the population would neither grow nor decline. It would stay at a constant value. All right. So what we've just seen is what we call geometric growth. Geometric growth occurs when a population has reached a stable age distribution, and when the population is growing or declining at a constant rate from one year to the next. So again, you saw there was a lot of wobbling around, and my age ratios were kind of bouncing around early on, and then they settled in to those constant values. Same with the population growth rate. It bounced all over the place for a while, but then it settled in at a constant value. So geometric growth, we can only really talk about geometric growth once we've settled in to those sort of stable systems where I have a stable age distribution and I have a constant rate of change in the population from one year to the next. When that's true, I can describe the population at year t plus 1 based on the population at year t. So I can describe the population size 1 year later based on the population now using this equation. It's a really simple equation. I just take the size of the population now, I multiply it by the population growth rate, and that gives me the size of the population 1 year later. And this is called geometric growth. And that constant, that population growth rate, when we have geometric growth, we call that the geometric growth rate or the finite rate of increase. All right. So again, here we have our two figures. On the left-hand side, we've plotted population growth rate as a function of time. And you see bouncing around crazy stuff at the beginning, but then it settles into a constant value right there. And once it's settled into that constant value, we can talk about geometric growth. We can use that equation. And what that equation, basically that value that the graph settles in at, that is the value of lambda. That's the value of our geometric growth rate, whatever the value of that sort of flat line. Now, what we can then do is we can predict the population change in size from 1 year to the next using this equation. So if I want to know the number of individuals in year 13, all I need to do is look at the number of individuals in year 12. In this example, it happens to be 67,395. Plug that in, multiply it by the population growth rate, which is a constant, and that's going to give me the number of individuals in year 13. If I want to know the number of individuals in year 14, then I start with that same number of individuals I just calculated in year 13, so that's 109, 180, and I multiply it by that constant population growth rate, again, where that sort of population growth rate curve flattened out, where it sort of stopped changing, and that gives me 166,872 individuals. And so I can keep predicting from 1 year to the next. I can keep predicting those red dots by taking the population this year and multiplying it by the population growth rate to get the population next year. And so again, this is my geometric growth rate equation. If I take the number in year 0, I can get the number 1 year later by multiplying by lambda. I can get the number going from year 1 to year 2 by multiplying by lambda again. I can get the number in year 3 by taking the number in year 2 and multiplying by lambda, and so on and so on and so on. Now, if you're clever, you'll look at this and you'll say, well, I might be able to sort of simplify some things here. If I take a look at my equation for the number in year 2, well, I can take my equation for the number in year 1 and I can just plug it in, just like that. And I simplify and I just basically take the number in year 0 and I take that multiplied by lambda squared. And then I can look at the number in year 3, and you'll notice I could take that equation for the number year 2 and plug that in and simplify that. And so to go from the number in year 0 directly to the number in year 3, I just have to multiply it by lambda to the power 3. And then to go to year 4, I can just take that equation for the number in year 3, plug it in, simplify, and I basically go from the number in year 0 to the number in year 4 by multiplying the number in year 0 by lambda to the power 4. And so I can keep going like that. And in fact, very generally, I can write the number in the tth year as a function of the number in year 0 simply by multiplying by lambda to the power t. And so these two equations are equivalent. They can do the exact same thing. We use the top one when we want to predict the number next year based on the number this year, when we want to go from one year to the next year. We use that bottom equation when we want to go from some initial year to some later year that is possibly many, many years down the line. So again, we use the top equation going from one year to the next. We use the bottom equation to go from the first year to a year many years later. All right, so when do you use geometric growth? When do populations follow geometric growth? Well, typically we use geometric growth for species that reproduce synchronously at regular time periods. So if I think about June bugs, these are the things that you see flying around typically in May, June, because that's when they breed. And they only breed once a year. And so all we really need to know about is sort of what happens in a very short amount of time in that one year, and that takes us to the next year. That takes us to the population in the next year. So this is true of many insects in seasonal environments. It's also true of many birds. They have a sort of 1 month or 1 week breeding period where they, all the babies hatch all at once and they're all there. It can also happen in mammals. It's very typical in seasonal environments. And so what I'm going to do now is look at an example of a June bug. And we're actually going to use the geometric growth rate, or the geometric growth equation, that equation right there. We're going to use that to figure out basically how populations of June bugs are changing and how many June bugs we might predict down the line a few years later. Again, if you're not in class, I'd encourage you to try this problem on your own, and if you can't do it, I'd encourage you to either talk to me or find some friends who took notes. All right, so that's geometric growth. And like we said, that we use geometric growth when we want to go from one year to the next as sort of a single leap. In June bugs, that single leap is because they all breed at once in 1 month, and that takes us to next year. And then they'll breed again the next June, and that takes us to the June after. But if you think about it, that's not true of all species. So things like mosquitoes, fruit flies, the cockroaches that live in your house, these things do not sort of breed all at once one time during the year and then sort of do nothing in between. So unfortunately, mosquitoes are always breeding. Anytime you leave some water in your backyard, there's going to be baby mosquitoes in there. You leave water in your backyard for 1 day, there's baby mosquitoes. And that's because these species reproduce continuously. They have what we call overlapping generations. So when the adults of one generation are around, there's babies of another generation, and everybody's just always having babies. That's true of humans too. And this is true of a lot of organisms, particularly in more tropical environments where you don't have that seasonality, where you don't have that single brief pulse of breeding for the whole year. So unfortunately, with these continuous breeding species, we can't really describe them as easily with the geometric growth rate equation because there's just always babies around, and there's always sort of 1-day-olds and 2-day-olds and 3-day-olds and 4-day-olds and 1-week-olds and 2-weeks-old. They're just all sorts of ages all the time. And for these, we use calculus. Basically, the calculus that the calculus equation that corresponds to geometric growth, that corresponds to that really rapid increase in a population size, is what we call exponential growth. And the differential equation, you don't have to know how to use this, but the differential equation that corresponds to exponential growth is what you see on the slide there. What you do need to know how to use is the integrated equation right there. So this is, again, very similar to the geometric growth equation. It's going to tell us the number at some time point later based on the current number of individuals in a population and the rate at which the population is growing. All right. And so that little r, that is what we call the exponential growth rate, or the intrinsic rate of increase. So this is different from the geometric growth rate. They're related, but it's going to be a different number. So again, when we are using continuously breeding species, and we have this equation that comes from calculus, that little r is what we call the exponential growth rate. All right. Now we're going to use that exponential growth rate equation to do, again, an example calculation where we look at growth rates in tribbles. And again, if you do not know how to do this, or if you try this and you can't figure it out, I encourage you to get someone else's notes or to talk to me. All right, so that's geometric growth and exponential growth, and it's a little easy to get the two confused. So we use geometric growth when we have discrete time, so when we have sort of a single breeding window. We use exponential growth when we're thinking about continuous time, when things are always breeding. Humans are always having babies. You can never go to the hospital without finding babies. That's not true, again, of things like birds, where they only nest in the spring. So again, we use geometric growth when we're thinking about reproduction that occurs at regular time intervals, and we use exponential growth when we're thinking about reproduction that occurs just all the time. This is our equation for geometric growth. This is our equation for exponential growth. Now, if you look at these and squint, you'll notice that they're kind of similar. So both of them have a term for the population size at time t. Both of them have a term for the initial population size at time t equals 0. And then both of them have this other term. Now, not surprisingly, we can relate these two equations based on that other term. And so what you'll notice is that lambda should equal e to the power r. If we do that, then these two equations are kind of the same. Same kind of deal. R then is equal to the logarithm of lambda. I've just taken the logarithm of both sides. And so this is how geometric and exponential growth equations are related. They're related. Lambda is not equal to r. The geometric growth rate is not equal to the exponential growth rate. They're different numbers, but they're related according to these equations. So if I know the geometric growth rate, I should be able to predict the exponential growth rate. And if I know the exponential growth rate, I should be able to predict the geometric growth rate. Okay, that's weird. Why are these things related? Well, exponential growth occurs through time. And so the blue line in the figure there is sort of the exponential growth. It occurs continuously, and you see sort of this continuous change in the population, smooth change in the population as you go from year 0 to year 25 and sort of all the time points in between. Geometric growth occurs at these discrete time points, but those time points, those red dots where we can predict the population in year 12, 13, 14, 15, 16, you'll notice they follow the exponential curve. They lie exactly on the exponential curve. And so that's why the exponential curve is really just a lot more detail, but it's giving you the same trend. It's giving you the same change in population as the geometric curve does at the specific year points. You'll notice that there's no values at non-year points, sort of at year 12.5 or year 12.75, there's no value of the geometric growth curve. There's no sort of those just red dots on the years, and there's nothing in between the years. Whereas the exponential, because it's continuous, you have values all through, even at year 12.5, year 12.6, year 12.7. The exponential curve is defined because it's continuous. Because the exponential curve is continuous, you can use it to predict the population sizes at discrete time intervals, at year 12, at year 13. Because the geometric equation is not continuous, you cannot use it to find population sizes at continuous time intervals. You cannot use the geometric equation to find the population size at year 12.5 or year 12.2 because it's just not defined there. It's only defined at discrete time intervals. All right, but again, these are related. So if I take a look at my geometric growth equation, let's suppose I have a population where my geometric growth rate is 1.5 and I begin with 10 individuals. Well, then 1 year later, I would expect 15 individuals. 2 years later, I'd expect 22.5 individuals. 3 years later, I'd expect 33.8 individuals. Now, to use the exponential equation to predict the exact same thing, I need to convert from my geometric growth rate to my exponential growth rate, but that's easy. I just take the logarithm of my geometric growth rate, and that gives me my exponential growth rate. And then I start with the same 10 individuals. And again, if I predict the population size 1 year later, I get 15. 2 years later I get 22.5, and 3 years later I get 33.8. So they're exactly the same. As long as I convert lambda to r and r to lambda, I should get the same exact values at year 1, year 2, year 3, year 4, year 10, year 100, should always be the same. The difference is, if I want to know what's going on at year 2.5, because I have a continuously breeding population where I expect a change between year 2 and 2.5, then I have to use the exponential growth equation, because the geometric growth equation says nothing happens until I get to year 3, right? I have breeding at year 2 and then nothing happens at all until I get to year 3 when I have another pulse of breeding. And so if my population is actually breeding all the time, then I do expect a change between year 2 and year 3. I expect it to be different at year 2.5. I expect growth to occur between year 2 and year 2.5 and year 2.5 and year 3. I can't predict that with the geometric growth equation because it ignores anything that might happen between year 2 and year 3. It says nothing happens, there's no breeding until I hit year 3, and then I have a pulse of breeding. Okay, and so that's how they're related. Okay, so here are my two graphs. I sort of have my exponential growth curve in blue. I have my geometric growth points in red. And that figure on the left is what we've seen before. That shows you the rate of the total population size as a function of time, and you see it's really blowing up. The other thing you can do with these graphs is you can actually take the logarithm of the population size and plot it against the time, and you'll get a straight line. And the important thing of this is that that straight line is going to tell you the population growth rate. And so the slope of that straight line is the exponential growth rate r. So in this particular example, I can calculate the slope, and it's 0.482. And then, of course, if I want the geometric growth rate, I just convert between my exponential growth rate and my geometric growth rate using that equation from the previous slide, and I get 1.62. All right, so we've talked about exponential growth, we've talked about geometric growth, we've given examples of how to use those equations. The final thing we're going to talk about is doubling times. And some people get confused with doubling times, but they're basically sort of analogous to half-lives in chemistry. So if you did half-lives in chemistry, it's sort of the same idea. And they're really just one example of population growth. So if I have a cockroach population and I have, say, 1, 2, 3, 4, 5, 6, 7 individuals, then at some point that population is going to reach 14 individuals. And so it's doubled in size. It's gone from 7 to 14. And then the doubling time is how long it takes to do that. To figure out the doubling time, it's really quite simple. You don't need to memorize a new equation. You just take your exponential growth rate equation and you say, okay, well, if I started with a particular number of individuals, how long does it take me to get to twice that number? 2 times n0, and that's my doubling time, td. And I can sort of divide the n0s away from both sides of the equation. I can take a logarithm and basically just rearrange, and that gives me this equation for my doubling time. Basically, to know the doubling time of a population, I just take the log 2 and I divide it by the exponential growth rate of the population. So in this particular example, to find my doubling time, I basically take the logarithm of 2, divide it by 0.482, and it gives me 1.44 years. So that tells me that the population doubles in size every 1.44 years. So again, if I had a population of 1 times 10 to the 7, then double that population would be 2 times 10 to the 7, and what you'll notice is that it does indeed take about 1.44 years for that population to double. And it would take another 1.44 years to reach 4 times 10 to the 7 for the total population size. All right. So we're going to do one more example, this time with doubling times, and it's going to be exactly the same sort of system as before. We're going to look at doubling times for triples. And once again, because we're doing this in class, I'd encourage you, if you weren't in class, to work through this example on your own, and if you can't figure it out, to ask friends or ask me. And you can ask me by sending an email to sbewick@clemson.edu. You can talk about the practice problems or any other questions you have about today's lecture.